Hello everyone, my name is Kabileshkari and I'll be presenting on memory compression in modern operating systems, specifically how it works in Windows 10. This mechanism plays a crucial role in optimizing memory usage, especially in systems with limited RAM, like embedded devices and mobile devices. Let's get started. To understand memory compression, we first need to revisit how traditional memory management works in most operating systems. Modern OSs use virtual memory, which allows processes to operate as if they have access to a large continuous block of memory, even if physical RAM is limited. This abstraction is limited using paging, where memory is broken into 4 kilobytes blocks called pages. When RAM is full, the operating system must decide which pages are less important. These are usually inactive or least recently used pages. It removes them from physical memory and writes them to page file or swap space on disk. This process is known as paging out or swapping. Now here is the catch. Accessing a page from disk is orders of magnitude slower than accessing it from RAM, often by a factor of 1000 or more. That's why if your system is frequently swapping, it becomes noticeably slow. Not only does swapping hurt performance, but it also leads to increased disk input and output operations, higher power consumption, and on the SSDs, accelerated wearing and tearing. This is especially concerning for mobile devices and embedded systems. So, to tackle this, modern operating systems like Windows 10 introduced memory compression. Instead of writing data to disk, the OS compresses the pages in the RAM and keeps them there, allowing more data to fit in memory and avoiding the performance penalty of paging to disk. Memory compression is a modern OS technique where instead of swapping out memory pages to disk, the operating system compresses those pages and keeps them in RAM. Now let me draw your attention to the Windows Task Manager screenshot. If you look closely at the bottom left, you will see the line labeled in use compressed. Here it shows that out of 14.8 GB of active memory in use, 1.1 GB is compressed. That means 1.1 GB worth of data is actually occupying less space in RAM. Thanks to compression, without this the system would either need more physical RAM or would be forced to swap disk, leading to performance degradation. This compressed memory is held in a special area called compression store, which resides in the system process address space. It allows the OS to defer swapping, keeping the performance high even under memory pressure. Also, notice that total memory used is 14.8 GB out of 31.3 GB available. So, although we have RAM headroom here, Windows has still chosen to compress memory proactively. This shows that compression is adaptive. It's not always about saving space, it's about staying efficient. Compression offers several key benefits. First, it reduces expensive disk input and output, keeping both active and inactive data in RAM. It also faster to decompress than loading from the disk. Reducing disk writes helps extend SSD lifespan, which is critical in embedded or low-end systems. And since disk access consumes more power, memory compression is especially useful in mobile or battery-powered devices. Alright, before we get into the actual compression process, let's get familiar with some of the key terms that come up in a lot in memory management. Let's start with the working set. Think of it as the set of memory pages that a process is actively using, kind of like the tools you have laid out on your desk while working. When the OS sees that RAM is getting tight, it tries to clean the disk by putting away pages that haven't been used in a while. This is called trimming the working set. Now, what happens if your program suddenly needs a page fault that was trimmed? That's a called that's called a page fault. And there are two types. A soft fault is actually not too bad. It means page is still in the RAM, just not mapped to your process anymore. So the OS just updates mapping quick and painless. But if it is a hard fault, that's a different story. That means page is gone from RAM and now the OS has to go dig out from the disk, which is way slower. And then we have modified list. This is where OS puts pages that were trimmed but had changes. So they are considered dirty and have to be either returned to the page file or, if memory compression is active, compressed and kept in RAM. Let's move on to the other list the OS uses to manage memory like a pro. First, the standby list. This is basically a memory cache. These are clean pages that are not in use right now, but they were used recently. So the OS keeps them around just in case you need them again. It's like having your recent tabs saved. You might go back to them, and if so, you avoid the pain of reloading from disk. Now the free list. This one's simple. These are pages that are completely empty. They are not holding any data, not mapped to any process, nothing. If a process needs memory right now, these pages are ready to go, no cleanup is required. And finally, the compression store. This is the interesting part. Instead of sending the pages to disk when memory is tight, Windows compresses them and keeps them in a special area in RAM. This area lives inside the system process address space. Think of it like a zip folder inside a RAM. The data's still there, just smaller. So if a process needs the data again, it can be decompressed right from RAM, which is way faster than pulling it from the page on disk. That's what makes memory compression so effective. It's clever middle ground between keeping everything in RAM and dumping everything in disk. Alright, so now let's really zoom into what happens inside the memory manager when things start getting tight. Imagine you are the OS and RAM is your house. Space is running out and you need to decide what to clean up. The first thing the OS does is look at each process working set. Basically, it's active disk space. If memory pressure is high, Windows start trimming, moving the less used pages off the disk. It doesn't throw them out right away. It tries to be smart about it. Let's say a page has been modified. The process changed the data, the page is considered dirty, and moved it gets moved to something called the modified list. Now here is the fun part. If compression is enabled, instead of writing that dirty page to the page file on disk, which is slow, the OS compresses it and drops it into a little zip pack called the compression store, which lives in RAM. If compression isn't enabled, it just gets returned to the page file as usual. But writing to disk is like mailing a letter across the country versus passing a sticky note to the person next to you. It's slow. Now let's look at another kind of page, the clean kind. Maybe it was just read or executed but never returned to. These go to the standby list. Think of it that like your browser tabs. You haven't used them recently, but you might come back to them. If process accesses it again, that page can be just remapped immediately. That's called a soft fault, and it's super fast. No disk, no decompression. But here is the beauty of memory compression. Let's say the process needs a page that was compressed earlier. Instead of going all the way to disk, the OS just finds it in the compression store. decompresses it, and gives it back to the process. Again, it's a soft wall, just a more compact version of it. What if the compression store itself starts getting full? The OS has to make judgment call. It might take some of the least used compressed pages and finally send them to the page file, or just discard them if they came from files and can be reloaded later. It's always balancing performance and space. Now, in some cases, none of this is enough. Maybe the page was evicted long ago and isn't in RAM at all. That's when you get a hard page fault, and that's the slowest scenario because it means the OS has to pull the page from the page file on the disk. On the flip side, if memory pressure goes away, say you closed some heavy apps, Windows stops compressing. No need to waste CPU on compressing memory that fits just fine as is. So to wrap up with an analogy, memory compression is like vacuum packing clothes. You are not throwing them away, you are just shrinking them so more can fit, and when you need something, you unzip it way faster than digging it out of the storage unit across the town. You can actually see this in action right now. On your own system, just open Task Manager, Performance tab, then click on Memory and look for the compressed value. That's the magic in play. So let's talk about the real benefits of memory compression, not just technically, but from user's perspective. First, it reduces the need to swap pages to disk. That means your system stays responsive even when you are running memory heavy applications. You can have your IDE open, a browser with 30 tabs and maybe even a virtual machine, and still feels snappy. More pages fitting in RAM is key. Compression lets 1.5 to 2 times more inactive data live in memory without affecting the active performance. And it's faster than disk input and output operation. Even the fastest SSD are much slower than the RAM. With compression, you're trading the input and output latency for a little CPU time, and that's actually a good deal. You are also extending the life of SSDs, which is especially valuable on laptops or any kind of embedded systems that don't get frequent hardware refreshes. Lastly, this is a huge win for embedded or low memory devices like IoT hubs, smart cameras, or even Raspberry Pi projects. Compression lets you squeeze more performance from tight memory budgets, and that's what I really like, that it's a adaptive Windows only enables compression when it's actually needed. So it's a smart enough to help but not get you in your own way. Now you might be wondering, if memory compression is so useful, why wouldn't Windows always use it? The answer is compression has a cost. It takes CPU cycles to compress and decompress memory pages. So if the system already has plenty of free RAM, Windows doesn't bother. There is no point in compressing data if it can stay uncompressed without causing pressure. Also, in some cases, like CPU heavy tasks or real time applications, adding compression might introduce latency, so the OS skips it to keep the performance smooth. Sometimes the page data is already compressed, or compressing it doesn't save enough space to be worth the effort. And of course, memory compression is only available on Windows 10 and newer. You won't see this in older versions unless you are using the custom solutions. So memory compression is not always on, it's adaptive, used only when it provides a real benefit. Compression isn't just theoretical, it's everywhere, from your Windows laptop to Android phones and even embedded Linux devices. It's particularly powerful in VMs and cloud platforms, where saving RAM across hundreds of instances adds up to real cost savings. So to wrap it all up, memory compression is one of the smartest tools modern operating systems use to make the most out of the limited RAM. First, it helps reduce swap usage. which means fewer slow trips to the page file on the disk. That alone can make your system feel more responsive. Second, it speeds up the memory management by letting the OS keeps more data in RAM, even if it's compressed. This helps maintain performance under load without sacrificing memory availability. And third, it's a huge win for low RAM and embedded systems, places where memory is limited, but still performance matters. What I really find interesting is how adaptive this feature is. Windows only uses memory compression when it senses memory pressure. It's not always on, and it won't waste CPU if it doesn't need to. All in all, it's one of the best invisible optimization added in modern operating systems. You won't see it working, but you will definitely feel the difference, especially when the system is under pressure. That brings to the end of my presentation. I hope this gave you a clear and insightful understanding of how memory compression works and why it's such a powerful optimization in modern operating systems. Let's wrap it up. Thank you so much for your time.